Hello viewers, welcome to my channel KK Concepts of Electrical Engineering.
Energy stored in magnetic field. We know that an inductor L having the inherent property of electrical inertia or inductance, which is going to oppose the change in the current's magnitude according to the Lenz's law. So energy is not going to store in the electrical field, but it is going to store in the magnetic field. Similarly, in a capacitor, if you observe, energy is stored in electric field. Now, E equals to N d phi by dt. When you multiply this with I by I, then you can write this that N phi di by dt divided by I, which is nothing but N phi by I is equals to L di by dt. This is E in case of inductor poles. What must be done in order to force the current through an inductor, since the inductor opposes the current's magnitude? As the current increases gradually from zero, the flux linkage of the coil changes every instant, and an EMF is induced. That EMF is given by this formula. Let the differential work done dW in dt time is given by dW equals to EI dt in joules. So let us substitute this value L di by dt I dt. Now dt gets cancelled, then differential work done is given by L I di. The total work done W equals to integral dW, that equals to integral Li di. So Li, if you do this, I square by 2, from 0 to I the current need to be increased, so 0 to I, then you are going to get Li square by 2 is the work done in joules. Total work done W is equals to Li square by 2 in joules. And we know that L equals to N phi by I, where N phi is nothing but flux linkage, that is lambda by I. If you substitute that L value in this, then you are going to get lambda I square by 2, then half lambda I. Other terms, we can write this lambda I flux linkage, that is into current divided by 2. On this, we can also write I equals to lambda by L. Now, if you substitute that, so this is going to be lambda square by 2L. In terms of inductance and the current, second term is in terms of flux linkage and current, third term is in terms of flux linkage and inductance. Energy density. We assume the energy is evenly distributed throughout the magnetic field. We found that energy in magnetic field is given by half Li square in joules. Consider an elementary volume dV inside the magnetic field, and the volume is a small cube. The elementary volume delta V is equals to delta L whole cube. We have H equals to Ni divided by L is the length. So in our case, N equals to 1, so I by L, that equals to delta I divided by delta L, since considered this as elementary volume, so elementary current will be there. We know that delta L is equals to mu delta small l is the length. From this, delta I equals to H delta L. For our elementary volume, the elementary work done, delta Wm is given by half delta L delta I whole square. Now substitute the values of delta L and delta I from these two equations, then you are going to get half mu delta L small l, this is the length, delta I is H delta L, then whole square, so square, then half mu h square. Delta L into delta L square is nothing but delta L cube, which is nothing but a delta V, that is nothing but volume. This is in joules. Energy density is given by limit delta V tends to 0, delta Wm divided by delta V. So when you apply that, you are going to get from this equation, that is delta omega L divided by delta V is nothing but half mu h square. Magnetic energy density Wm is given by half mu h square.
If you have any suggestions and queries, please mention in the comments. If you like this video, please like, share and subscribe. Thank you for watching the video. Please stay tuned for more videos.